So it's a great pleasure to introduce Cynthia Dwork from Harvard University, or currently at Harvard. With AI moving from academic research, from an academic research topic to real-world applications, AI researchers are faced with important new questions concerning the recommendations and decisions proposed by AI systems and machine learning models. Issues of data privacy and algorithmic fairness are now being discussed on the front page of the New York Times, and it's clear that these topics need serious attention from our research community. Cynthia is arguably the best qualified computer scientist to lay the foundations for how to address these challenges and move us forward to resolving the core research questions. Her work on privacy-preserving data analysis provided the first truly rigorous mathematical foundation for studying data privacy issues, which created a whole new subfield around the notion of differential privacy. In her most recent work, she is addressing the challenge of algorithmic fairness. Over her career, Cynthia has made foundational contributions to an impressive range of core challenges in databases, cryptography, and distributed computing. The only drawback I can see of receiving a list of major honors as long as Cynthia's is that the person introducing you will have to struggle with the question of whether to list them all. So I'll just mention a few. Cynthia's work on differential privacy was recognized with the 2016 Theory of Cryptography Conference Test of Time Award and the Goedel Prize. She also received the Dijkstra Prize for a contribution to distributed system and fault-tolerant computing, and she's a member of the US National Academy of Sciences, the National Academy of Engineering, American Philosophical Society, and a fellow of the American Academy of Arts and Sciences. So, without further ado, please join me in welcoming Cynthia.
Thank you. Okay. Good morning. I think that Bart did an absolutely perfect job of motivating the topic. So let me just add that the increase in interest in developing notions of fairness is due to the fact that algorithms are reaching increasingly into our lives and affecting the options which are presented to us. So the concern in this talk is going to be bias. We have a population. Our population is diverse, and it has subgroups that divide along ethnic, religious, physical conditions, medical conditions, and class lines, for example. And algorithmic bias can arise from many different sources. One of them, of course, is historically biased training data, or training data that, that has pockets of ignorance as different subgroups move into a population. So the focus in this talk will be on classification algorithms. I mean, algorithms are used in many different ways. We're going to focus specifically on classification, and mostly I'll consider labeling people as 0 or 1. And again, the problem is the bias that's embedded in the training data. So here's our general framework that we have in mind. We have a bunch of individuals, and they're this diverse population. And we have a classifier that maps individuals to outcomes. And you can think of outcomes in a very broad sense. And the classification is done on behalf of a user. So for example, the user could be a bank that's trying to classify people not just as to whether to give them the loan or not, but perhaps which set of terms to offer. The user could also be an admissions committee that's trying to decide to accept or reject students, but also perhaps what sorts of financial aid packages to offer. Or the user could be an advertiser who's trying to determine which of a small collection of ads to show this person, or whether to advertise to this person or not. And each of these is a different kind of classification task, and each one will require its own classifier. Now, we have the classifier. it maps individuals to these classification outcomes, and the user only sees the classification outcome. So for example, in the advertising setting, individuals may be mapped to one of some dozens or hundreds even of bins that have cute names like struggling second city new parents or white picket fences. And I didn't make these up, these. No. Okay, and the only thing that the advertiser sees about an individual is which bin has this person been placed in. So they've been categorized. So in some sense, if we have fairness in mapping people to the bins, then we don't, everything else follows by post-processing. So if we have fairness in our basic classification step, then we don't have to worry about what it is that the user does. The user can map these outcomes to any arbitrary action. So this lets us focus on the core problem, which is just the classification, and let's forget about what the user is actually doing. Okay, so together with my collaborators, Moritz Hart, Tony Patassi, Omar Reingold, and Rich Semmel, we started thinking about this in about summer of 2010, I guess. And, well, we did what anybody with training in cryptography would do. We sat down and we said, what is the problem that we're trying to solve? How do we get our hands on that? The way we get our hands on that is we think about an adversary, an unfairness adversary who is basically trying to do evil. So what are the kinds of things that an evil adversary might do? Well, it might try to redline, which is basically to deny services, either directly or through selectively raising prices, to residents of certain areas. And this is a famous redlining map from home lending. Or they may try to do some sort of reverse tokenism. You turn me down for a loan, I say, oh, you don't like people with curly hair, and you point to somebody with straight hair and say, this person is obviously better qualified than you are, and we've turned him down. So how can you say that we're discriminating against you on the basis of curly hair? But the problem is that they use that same person for all of the people that they turn down. So they turn down one straight-haired person and all of the curly-haired people. Or it may be a question of deliberately targeting, for the advertising case, the wrong subset of a minority group. So for example, you're required to show ads equally to people in the minority group and proportionately to people in the minority group and the majority group, but what you do is you show the ads to people in the minority group who cannot pay to come to your fancy spa. So you've sort of taken care of your representation issues, but you're clearly not being fair. So anyway, we sat down and we wrote down a catalog of evils, and then we tested various solution concepts against these catalog of evils. Now, the first thing that many people think of when you talk about fairness is called sometimes statistical parity. So statistical parity says that for any classification outcome O, the demographics of people that receive label O is the same as the demographics of the population as a whole. Okay, so if a third of your applicants belong to a minority group, then a third of the people who are accepted will belong to the minority group. There are other group notions, before I get into statistical parity, there are other very natural group notions. So for example, in the case of recidivism prediction, which we'll talk about in a moment, you might want to have equal positive, false positive rates across groups. So the false positive rate is the fraction of negatives that are erroneously labeled yes. So it's the fraction of people who are not actually high risk that are erroneously labeled as high risk. Or you might require equal false negative rates across groups. Or perhaps equal positive predictive value across groups. That says, among those who receive the label yes, the fraction that are actually going to be to recidivate should be about the same across groups. And you might want some kind of conditional parity or equalized odds, which says that the probability that you get mapped to outcome O, given that the truth is O, is the same across groups. And there are other group fairness notions. These are some that show up a lot in the literature. So let's look first at statistical parity. When you start thinking about trying to be fair, one of the first suggestions that's made is just don't let the algorithm see the sensitive attribute, whether the sensitive attribute is sex or sexual orientation or race or religion or income, things like that. And of course, the problem with that is that the sensitive attributes are often sort of holographically embedded in the rest of our data. So my ethnicity may affect what kinds of music I like, what kinds of books I read as a child, and so on. So the demographics of a selective group being the same as the demographics of a population actually ends up neutralizing these redundant encodings. So that's terrific. That's a real plus. On the other hand, it does permit several evils in the catalog, as I said earlier with respect to the SPA. So it permits intentionally targeting the subset of your minority group that's unable to pay. So it's not a good solution concept in general, although it has a nice property of handling holographic encodings. Another problem with statistical parity is it may give you low utility on your subgroup when multicultural awareness is low. So the example that we give in the paper is, suppose in your minority group, or in your subgroup, which might not actually be a numerical minority, the brightest members are steered by their parents and culture toward careers in math and science. And the less good members, let's say, are steered to finance. And suppose in the majority culture, it's reversed. So the brightest members of the complement of S are steered toward finance, and the less good to these other careers. So if you wanted a quick and dirty classifier for finding bright students, and actually, yeah, in this case, it really is a minority, it's a small minority, then you could have a classifier that was based simply on studying finance. Because if the majority is really a majority, it's only going to be wrong on the minority, which is a small subset. So that works in some sense, but obviously it's missing out. Not only is it unfair, but it has reduced utility on S. And what this shows us is that you don't want to hide membership in the minority group from the classifier. And you want your classifier to have some sort of multicultural awareness and to understand that for the purpose of finding bright students, members of S that study math and science should be viewed as similar to or close to members of the majority group that study finance for the purposes, again, of the bright student classifier. So we want some kind of a cultural awareness in our classification process. So that's a problem with the specific statistical notion or group fairness notion of statistical parity. Now, what about the other notions? So as many of you probably know, there's a famous incompatibility among some of them. So ProPublica published a study about a recidivism prediction algorithm called Compass from the company Northpoint, and showed, looking at the data, that there was a disproportionately high false positive rate for blacks and a disproportionately high false negative rate for whites. So it was sort of erroneously predicting that blacks would reoffend, and it was erroneously predicting that whites would not reoffend. So in some measure, which is something we'll come back to much later, these are both errors that sort of relatively benefit whites over blacks. And when they said this, Northpoint more or less responded in not these words, but we are test fair. That is to say, and I'm simplifying, the positive predictive value, the probability that you actually will recidivate, given that we say you are high risk, is the same for both blacks and for whites. So what this means is you can take the score or the outcome completely at face value. You do not need to interpret it in light of your of the individual's race in order to understand what it means. It has exactly the same meaning across race. So maybe it is fair, at least with this definition. And in two independent papers for variants of this problem, I'm giving the simpler version here, Chuldachova and separately Kleinberg, Mullainathan, and Raghavan showed that no imperfect classifier can simultaneously achieve these three desirable goals of equal false positive rate across group, equal false negative rate across group, and equal positive predictive value across group. And these three quantities are related by the expression on this, the equation that I'm showing you. So imagine that you had two equations. They were identical, but one is for blacks and one is for whites. And you require equality for the corresponding blue terms. Then the red terms have to be equal. So if P is the base rate of reoffending in the population, then P would have to be equal. So no imperfect classifier, one that has false positives or false negatives, can simultaneously ensure these things, unless the base rates are equal. Okay, so group fairness sometimes makes sense, sometimes is problematic. What's an alternative? So an alternative is a notion of individual fairness that I hinted at earlier. It says that people who are similar with respect to a specific classification task should be classified similarly. Now, there is, in the individual fairness work, a science fiction component. We're assuming that there exists a metric, D, that tells us for a pair of individuals how similar or dissimilar these people are for this particular classification task. Now, I should note that while we call this out as science fiction, this kind of thing is implicit in many systems. So for example, credit scores induce a metric, and you would expect people with similar credit scores to be treated similarly. If they have very different credit scores, you have no particular expectation of similar treatment. Okay, so I have a feeling that individual fairness captures many things that people actually feel. So I may feel that I was discriminated against in an employment decision, and I may not be comforted by knowing that women in general are given offers at the same rate as men. For example, I may feel that, nasty women aren't given offers, and submissive women are. And there is a discrimination component, even though the groups are the numbers may be similar. And so I think that part of what sets us off is this, sets off our sense of outrage, is the sense that somebody who is very similar to me, I view as very similar to me, received very different treatment. So, yeah, okay. And in our work, Fairness Through Awareness, we adopt individual fairness as our basic approach to fairness. Now, let's think about credit scores. So suppose credit scores are sort of uniformly smushed from, high of, 800 down. And you may feel, well, we have to draw the line somewhere. But if you do that, you may have two people, X and Y, where X is just slightly higher credit scored than Y, and X gets loans and Y doesn't. And so how are these similar people being treated similarly? So as computer scientists, we certainly know how to deal with this. We randomize. So what we require is that now, instead of mapping an individual to an outcome, we map individuals to a probability distribution on outcomes and require some kind of Lipschitz condition. If we look at the two different probability distributions assigned to individual X and individual Y, and we take some measure of this difference, such as, for example, total variation distance, then we want that the distance should be bounded by the distance between X and Y in the underlying metric. So that's the fairness condition. And for those of you who know differential privacy, there is a flavor of differential privacy here, where we require that databases that are very similar should give rise to similar distributions on outcomes. Here, we're requiring that people who are similar for a particular classification task should receive similar distributions on outcomes by a classifier for that task. A classifier for other tasks may treat them completely different because they may be totally different from one another with respect to this other task. Okay. So getting back for a moment to statistical parity, suppose we did manage to ensure this individual fairness. What would it say about statistical parity? Would it happen as a consequence? And the answer is that this will ensure statistical parity if and only if the distribution on the groups is very similar, that they're close in earth mover distance, where the underlying metric is our metric for this task-specific metric. So if you have two populations that are very similar, then you'll get statistical parity from individual fairness. Otherwise, you may not. And that makes a lot of sense. And I think it also tells us a little bit about some of the thinking when you look at group fairness notions. That I think some of the thinking is that if you look at large groups of individuals, really large groups of individuals, then the groups are fundamentally the same. Intelligence is fundamentally distributed the same way across large demographic swaths. And so you expect some kind of statistical parity, and when you don't see it, it acts as a flag. Okay. Now, let's go back to the recidivism example. So let's look at individual fairness in the recidivism example. What should be the right metric here? One way of modeling this is we have an individual, X. X interacts with the environment. There is randomness inside of X. Maybe this captures health conditions of X, whether X is going to come down with one disease or another, or mood problems or whatever. And then there's an environment, and there's randomness in the environment. The employer lays off a bunch of workers, a family member gets sick, and so on. So we can define a probability. We can't necessarily measure it, but it's at least well defined. A probability over the randomness in both X and the environment that X will recidivate. And then individual fairness would require that if pi X and pi Y are similar, are close to each other, then X and Y should have similar probabilities of being classified as high risk for recidivating. So it makes a lot of sense. And when you look at it, see, I don't think that people have a hidden bit inside them that says I am necessarily going to recidivate. I think often that is not the case. And what happens is recidivism happens in part because of interactions with the environment. And we know that the environment is more hostile to blacks than to whites. And in fact, there's a study by Diva Pager, and I'm sorry I forgot the other authors, showing that for certain kinds of jobs, white men with criminal convictions are preferred over black men who have no criminal history. So the environment is much more hostile to one group than to another. And of course, looking at things through the lens of individual fairness can't circumvent the impossibility results of Choldachova. Obviously, those are impossibility results. But it does help us, I feel, in finding the locus of unfairness. Okay. And just as a comment, even if you have equal base rates and you still want to require equal positive predictive value, false positive rate, and false negative rates across groups, then it turns out the only solution is to treat everyone identically, to give them exactly the same probability distribution on predictions. Okay, so first open problem area. Where are we going to get these metrics from? I actually conjecture, although I don't know how to make this conjecture rigorous yet, that if we have a system of classification that people really find to be fair, then you can extract a metric from that system. And by here, I use the word extract as in the cryptographic sense, that by interacting with the system, you can actually start writing it down. So, first open problem area is, how do we use machine learning and artificial intelligence to find the metric, to determine what the metric is? Okay. Now, let's vary the recidivism case. So suppose you have a company, Nasty News, that is, has a hostile working environment for women. And now, we let pi x be, let's say, the probability over the randomness in x and in the environment that x will succeed at Nasty News, where perhaps success is defined by staying in the job for at least 3 years and having at least one promotion during the first 3 years. So is that, in fact, the right metric? Should we be trying to predict success? If that's true, then what we're saying is that if pi x and pi y are close, then x and y should have similar probabilities of being hired. Except, well, is it hired? Is it, what should the metric capture? Your probability of success or your talent? What is the right thing? So what this example is showing us is that even though things are set up exactly as in the recidivism case, the math isn't completely telling us what we ought to be doing. That if this decision-making thing is in the middle of a pipeline that perhaps has bias before and definitely has bias afterward, we have to give a lot of thought to what it is that we're trying to measure when we make our decisions. And we also have to start thinking about how do we exert forces on the environment in order to equalize the playing field. Okay. Okay, switching gears a little bit. There's been a fair amount of work in the machine learning and deep learning community on fairness. And here is an example in work by Zemel et al. So the situation looks a bit like our previous picture, only now what we're trying to do is we're trying to find new representations for the data. So before we had some categories and we were mapping people to these bins or categories. Now we're trying to find some kind of representation of the data that does a few things. So first of all, we're going to look for some prototypes, let's say Z1 up to ZK. And we're going to use the softmax function to determine probabilities for mapping an individual to one of the prototypes. And the goal of the prototypes is that they should, first of all, forget group membership, which would yield some statistical parity. They should, in aggregate, through the mapping, preserve reconstruction of all the other attributes to the greatest possible extent. And they should preserve the labeling functionality that we're interested in. They should preserve the ability to learn how to label. Okay? And when you set this up, you basically describe a loss function that has 3 components. One of them penalizes divergence from statistical parity. One of them penalizes divergence from being able to reconstruct the rest of the attributes of X. And the final part penalizes failures in labeling correctly. And these are competing terms, and you do some searching over hyperparameters to try to find some kind of balance between them. So this work, which appeared in 2013, oh, right, okay, so side by side, in the, I didn't actually show you the fairness linear program that we used for individual fairness, but basically in individual fairness, you have a set of outcomes and you're trying to learn an appropriate mapping of individuals to these fixed outcomes. And we require unconditionally individual fairness. We can try in various ways. There are ways to insist also on statistical parity, and it requires this science fiction of a metric. In the learning fair representation, we don't have fixed outcomes. We're trying to learn these outcomes or prototypes, Z1 through ZK. We're aiming for statistical parity, and we abandoned individual fairness. But through that softmax, we still see that distances have to be meaningful. Euclidean distances have to be meaningful. Okay. Now, the learning fair representation approach was kind of brought into the modern era with a GAN-like variation on it. So here, the idea is to learn a censored mapping to a lower dimensional space. We have the sort of representation master who gets to choose weights for an encoder and a decoder. The encoder tries to hide sensitive attributes and to learn a classifier. And the decoder, so to learn a predictor. And the decoder tries to, again, keep the ability to reconstruct the rest of the individual X. But this is an adversarial setting, so that we're going back and forth with an adversary who's trying to distinguish encodings of members of your demographic group S from encodings of members of the complement of S. And they go back and forth as usual in an adversarial setting. And the key thing here is the intuition that if the predictor is not more powerful than the adversary, then the predictions will be relatively unbiased. If the adversary can't distinguish members of S from members of S complement, and the predictor is no more powerful than the adversary, then the predictions should be relatively unbiased. Okay. Now, the learning fair representations work and the adversarial version, and there are other papers that have similar flavor now in the literature, have all forgotten completely about individual fairness. I mean, there was some vestiges of it in the original learning fair representations paper, but that's gone now. And so I'd like to see that reincorporated into the deep learning approaches. Okay. Okay. So up till now, essentially everything that I've discussed has talked in some sense about a one-shot case. Like, we're going to classify people. But when you really think about how these classifications are going to be used, you need to think about some kind of composition. So for example, suppose you use a fair classifier to determine admission to school 1, and a fair classifier is used for determining admission to school 2. People don't go to 2 schools, but they need to go to at least 1 school. They only need to go to 1 school. So what about the or? If you used a fair classifier for school 1 and a fair classifier for school 2, then if you have 2 similarly qualified people, what will be the probability that, the difference in probabilities that these people got into at least 1 school? And I'm focusing on or because I think it's a very compelling example, and of course it extends to multiple ors of multiple terms. But other functions, you can look at other functions too, not just or. So the short answer is actually no. So this is a graph showing the probability that the or evaluates to 1 when you have 2 people which have an initial distance of 0.4 between them. In their distance in the metric is 0.4. So what happens is, if you did an or over enough terms, then of course they would both converge to 1. But they diverge for a while before they converge, and in this particular example, they're quite different from each other. So they're quite different from each other at, say, 3 and 4 and 5 levels of composition, degrees of composition. Okay. So I call that first kind of composition functional composition. And the function that I discussed here is an or. And in this picture, it's an or of multiple terms, 1, 2, 3, and so on, increasing along the x-axis. Okay. There's a more subtle composition issue that arises, let's first just discuss this phenomenon that was observed by Data, and Chance. So you have men and you have women. What did they do? They built a bunch of synthetic individuals that were all identical to each other, except half were synthetic men and half were synthetic women. And I mean that they created Google profiles for these synthetic individuals. Then they had all of the synthetic individuals follow the same script of visiting a bunch of employment-related websites, landing finally at the Times of India, which showed ads. And they looked at the difference in the ads shown to the synthetic men and to the synthetic women. So, and there was a discrepancy. And maybe you have a situation like this. Maybe what's going on is you have job-related advertisers, and again, this is just maybe, job-related advertisers that are willing to pay the same amount to show an ad to men and to women, and it's not a very big amount. At the same time, you have an appliance advertiser, let's say, that does not view men and women as similar, and in fact, pay very little to show their ads to men and a lot to show their ads to women. This is true. The attention of women is much more highly sought in advertisements than the attention of men. And gender expert Londa Schiebinger explains this simply by saying that women are frequently the shoppers for the entire family. So if you have a situation like this, where you're getting for men a bunch of sort of moderate bids, their attention, and for women you're getting moderate bids for the same jobs ads and some very big bids for the appliance ads, what would the ad network do? What will it show to women? So, choice composition basically arises when you have more tasks than you have slots. And there's a theorem which says that when you have any tasks T and T prime that have not identical metrics, and their metrics aren't trivial, and they're working on the same universe U of individuals, then there are individually fair classifiers C for task T and C prime for task T prime, so that if you compose them naively, as I just hinted at in the ad network scenario, they violate multiple task fairness. That is to say, there are two individuals, so that fairness, let's say, may hold for T for the system as a whole. If you look at the behavior of the system as a whole, the probability that the system as a whole shows U the ad for one job and V the ad for one job is bounded by, that should have, the correct bound, of course, was for the appliances, where the distance between U and V is very big and the constraint is not very severe. But it's violating the fairness condition for the other task. And in this particular scenario, if somebody was sort of qualified for both ads, the ad network has a preference as to which of the two ads they get, because the ad network wants to make money. But you can have other, the theorem extends to the case where the preference of what ad is shown is, when one is qualified for both of them, is determined by the individual, and still you get the same kind of result. So there is a simple solution that does give us sort of this fair choice composition. Fix any probability distribution you want on your different tasks. So in this picture, T has low probability and T prime has high probability. And now you choose a task according to this distribution. And now you use a classifier that's fair for that particular task T. You can show fairness for the system as a whole, individual fairness for the system as a whole. But this will require, in the advertising case, not advertising to many people. So sometimes people will just get no ad, which we might like, but it's not good from the point of view of the advertiser. It leaves a lot of money on the table. And by the way, while I'm describing this for ads, this kind of thing also applies to other sorts of settings. So open problem area 3, improve on the economics of the simple solution. So think about the system as a whole and find a way to do better than the simple global solution. Now, I've been discussing composition and what it does to individual fairness. But what about group fairness? And group fairness things also have the same problems. So, for example, in this picture, I have two distributions shown on the probability of a positive classification. So the probability that, yeah, okay. In the blue group, the sensitive attribute has value little a, and the various other qualifications have value little z. In the green group, they have the same basic qualifications, but the sensitive attribute is a prime. So in this particular picture, the expectation, if I choose a random person from the group and then I look at the probability with which that person is classified as positively, these expectations are the same in the two groups. That's what the picture is supposed to suggest. But this similarity will diverge under OR composition, just as we had divergence before. So this is conditional parity failing under composition. And the same thing also happens with choice composition for groups. So you may have sort of a motherhood tax example. You have home goods advertisers that aggressively pursue new mothers. And this is true. This is really what's done. So employment advertisers will lose audience. So one thing that they might do then is to target women who are not new mothers, restoring gender parity. But new mothers then are recruited less aggressively than men, and also than women who are not new parents. Their careers can stall, and this will erode their later prospects. So you do have the same kinds of issues arising at the large level that you have at the individual level. Okay. Now, the fairness notions that we talked about in the deep learning case, where we're sort of trying to erase the information about which group somebody belongs to or their sensitive attributes, you'd like to be able to use these in further future computations. So open problem area 4 is explore functional composition properties of fair representations and related. Okay. So wrapping up, this is, I think, a very exciting area, and it's very, very active. There are some really interesting connections to agnostic learning. So Kearns et al. And Hebert-Johnson et al. Require accuracy in expectation for large numbers of intersecting sets, very large numbers of intersecting sets. And you do have to think about the intersectional aspects of fairness. And they show, both of them in different ways, show connections to agnostic learning, which is negative in some sense. There are papers in bandit settings that explore the price of fairness, and they show that if you adopt a notion of fairness in which it's unfair to preferentially choose one arm, that means a population subgroup, over another if the chosen arm has lower expected quality than the unchosen arm, then you have there's an exponential gap in the regret, an exponential price. Work on decoupled classifiers is kind of fairness through awareness for groups, and it basically says we want to actually find classifiers for each group separately, and you choose a combination that penalizes, that minimizes a joint loss function, which penalizes group imbalance of various kinds and is also monotonic in errors. So it's better, the loss function shrinks as the accuracy improves. And there's a lot of work recently in causal notions of unfairness. And this is tricky because sometimes the fairness definition actually depends on the data generation model, but the data generation model may be hard to identify. And so it can be very brittle. So you know this saying that all models are wrong and some models are useful. That's what you have in the prediction world. It's not clear to me what's happening here in the unfairness world. And there are a bunch of philosophical issues that come up. So we can't just, much as I would like to, I can't just isolate the problem and say it's just the math right here. And so an example of this is pointed out by Burke, who writes about the consequences of leniency. When you're thinking about letting somebody out of jail on probation, what's the consequence of leniency when most violence is in fact intraracial, John Romer has very, very compelling thinking about the college admissions and medical school admissions and so on and so forth. Trade-offs, where his view is that you must invest in the education of disadvantaged children. You have to make up for differences in class and alcoholic parents and all sorts of things. And you have to compensate for them or try to compensate for aspects of the environment that are beyond their control. But he understands that there are two purposes of education. One of them is to sort of raise people up, and another is to provide trained workers for society. And so in his view, you compensate less and less as they get farther along in the education pipeline. Deborah Hellman argues that accuracy or correctness is the wrong lens through which to assess whether discrimination is wrongful. So discrimination by itself, she says, meaning that there are differences, is of course what decision making is all about. When is discrimination wrong, she asks. In her view, the key concern is when you're compounding a previous injustice. So an example would be charging higher premiums for medical insurance and life insurance to battered women, because indeed their risks are higher. But this is degrading and it compounds a previous injustice, she argues. Okay, and a lot of my understanding of this comes from conversations with a group of researchers and especially my student, Christina Alvento. Thank you.
So you mentioned the ongoing work in causal fairness.
I'm sorry?
You mentioned the ongoing work in causal interpretations of fairness.
Yes.
Do you think it would be possible to leverage some of the AI systems being built right now to answer the counterfactual question, what would history have looked like if there had not been bias?
I certainly hope so. You probably are more of an expert on what these systems can do than I am. But I do know that counterfactual notions of fairness, where fairness, again, depends on the model, can be problematic when you have two different models that give rise to the same distribution. But I very much like the question that you're proposing one study.
Thank you.
I think also, by the way, it's very, very important that these systems have some idea of history. So there's, I'm trying to think of the name. There's a book, The Color of Law, by Rothstein, that talks about whether US government policies are causally responsible, contributed to segregation. And it's a very, very important question because if there is no causal action on the part of the government, then there is no constitutional basis for redress. Whereas if there is causality, then there is this basis. But when you look at the lending records of, let's say, the last 30 years, you may not see the results of post-war discrimination that were explicit policy. So history has to come into these systems.
Thank you for the wonderful talk. I just wanted to ask about something you said early in the talk, which is that as long as we get the classifier to be fair, then everything is fair from that point on. And I imagine, for example, maybe I'm approving people for credit cards, and I'm doing a really fair job in that classification, but then I make the credit card product such that all the cashback bonuses are on products that are of interest only to the majority population. And of course, so that's still maybe unfair. So do you see many of these cases where, based on the decisions after the classification, you still get some level of unfairness?
I think when you frame the problem broadly enough to capture the kinds of things you just described, then almost surely it's an issue.
Thank you for a wonderful talk. I was wondering if you could say a few words about how bias in our input data can be sort of addressed. So a lot of the work that you've talked about today has been how we can solve making sure that our perfect data actually maps to a fair system. But oftentimes the data that we collect is inherently biased when we collect it, so we don't even necessarily know that.
Right, so I wasn't assuming that we had perfect data, but in individual fairness, I am assuming that we, let's say, continually make progress toward understanding the metrics, so I don't know how to do it, and this was sort of my first problem area of how do we employ artificial intelligence to help with that. And there are various techniques that people have used that involve massaging data or massaging labels or regularizing in certain ways. But I think we need something more powerful and more general.
Thank you.
Thank you.